Okay, so the next couple of slides we did in class really wanted to emphasize expected value versus probability. So if I said to you, hey, wait a minute, um, what is the probability of the workers working 2 hours of overtime? The answer to that question is 3/40ths, and that's all that you answer. You just look at where x is 2 and the probability of x is then 3/40ths. What if I said, what's the probability that the workers work 3 hours of overtime? Well, that would be 8/40ths, okay? So when you get these tables, oftentimes they simply ask you what the probability is. But when they say what is the expected value, that's when you have to start multiplying quantities. And what I have seen, sometimes they ask what's the probability and students start multiplying values. If it asks what's the probability, do not multiply values. Keep it simple. All you do is look up, if it says what's the probability of 5, you look under the P of X column, you go down to where X is 5, and you would say 7/40ths. Okay? So simple as that. Expected values is not quite so simple. For expected values, you have to take the probability and then multiply it by the value, which is the X. So what I would do to find the expected value, the number of expected hours of overtime in a week, is in every case I would multiply the X by the probability of X. So in the first case, the probability you get no hours of overtime is 9/40ths, so I'd multiply that by 0. For 1 hour of overtime, it's 5/40ths, so I do 1 times 5/40ths. 2 hours is 3/40ths, 3 hours is 8/40ths, 4 hours is 7/40ths, 5 hours 7/40ths, and 6 hours is 1/40th. So I would multiply all of those, and when I do, I come out with 0, 5/40ths, 6/40ths, 24/40ths, 28/40ths, and 35/40ths. 6/40ths for the last one. Then I add them all up, and that gives me 104/40ths. And then I simply do the division, and I come up with 2.6. So therefore, a worker can expect, that's the expected value, to work about 2.6 hours of overtime on any given week. Okay? So it's important that we go over some stop and starts whenever we do these things and make sure that you're trying them first rather than just watching me go over them. Here's a very similar question, okay? This time it's 20 students in a class that were sampled as to the number of questions they got wrong on a test. X represents the number of questions that were wrong. The probability of X is summarized in the second column. So in other words, of the 20 kids in the class, 3 students had none wrong. So that would be the probability of getting none wrong is 3/20ths. Probability of 1 wrong is 2/20ths. Probability of 2 wrong is 5/20ths, and so on. So let's have you compute the expected value. I didn't write it here, I'm sorry, but your job is to compute the expected value. Do a little stop and start. I'll go over the correct answers in a moment. Okay, so 0 times 3/20ths, 1 times 2/20ths, 2 times 5/20ths, 3 times 7/20ths, 4 times 1/20th, 5 times 2/20ths, 6 times 0/20ths. That's what I wrote there. Now I actually do the math, and that gives me 0 plus 1 times 2/20ths is 2/20ths, 2 times 5/20ths is 10/20ths, and so on. Then I add all of those numbers up, just like I did in the previous problem. Remember, with denominators and fractions, you keep the denominator the same. I get 47/20ths. And if I do 47 divided by 20, I get 2.35. So that means you can expect a student can expect to get 2.35 questions wrong on any given test. Okay? So those 2 questions were very important to go over because in my perusal of your work, what I found is that there were times when students confused the question, what is the probability, with what is the expected value. Whenever you talk about expected value, you have to take the outcome, in this case the X, and we need to multiply that by the probability of x. And then we add them all up, and then we just simply convert the resulting fraction into a decimal, and that gives us the expected value. Okay. So here's another question. In 2012, 1,664,479 students took the SAT exam. The distribution of scores in the verbal section of the SAT had a mean, mu, of 496 and a standard deviation of rho equals 114. Let X equal an SAT exam verbal score in 2012, and they give the notation, they describe this normal function as X tilde, N for normal, 496, 114. Remember that 496 is where the mean goes, that's what mu stands for. And the 114 is the standard deviation. So they say find the z-scores for 325. That's the first x. And the second x would be 366.21. And then interpret each z-score. Now, when we talked about z-scores, we said what a wonderful thing it is to have this formula to work off of and how it makes life so simple. So I mentioned having a folder on your phone or an album on your phone where you take pictures of important things and then with your phone, and then you put them in your folder. This is something I would definitely take a picture of. So let's do the z-score for x sub 1. In other words, when x is 325. So the z-score says the score in question minus the mean, which is 496, divided by 114. And if I just crunch those numbers, I come out with negative 1.5. If I do x sub 2 and I put in 366.21 minus 496 and divide by 114, I come out with negative 1.13. So what is the conclusion? How do they compare to the respective means and standard deviations? X2 is closer to the mean and it has a smaller z-score. Now remember, z-score is basically a representation of standard deviation or parts of standard deviations. So what this means is that x sub 2 has a smaller z-score, so it has a smaller, while the standard deviation value is the same, it's less standard deviations away from the mean. Okay? All right. So that's the review of work from the other day. We actually have time. I can do a couple of more slides on this one. Okay, so here's the normal distribution, a quick review of it the other day. This normal curve never changes, the percentages never change, and it's important to note that always in the middle of a normal distribution is the mean. The mean is always equal to the median because it's also the middle, and it's equal to the mode because it's the high point of the graph. So there's the most values at that point. And within one standard deviation of the mean is 68% of the scores. See, x plus mu, mu plus rho and mu minus rho. A rho is the standard deviation. So this is, mu is the mean, this is the mean plus 1 standard deviation, this is the mean minus 1 standard deviation. Within two standard deviations of the mean, plus 2 rho and minus 2 rho, are 95%. How do I know it's 68? Because 34 and 34 makes 68. How do I know it's 95? Because 13.5 plus 34 plus 34 plus another 13.5 is 95. Okay? All right, so having that knowledge and that graph to refer back to is very helpful. The scores on a college entrance exam have an approximate normal distribution, meaning it looks like the curve we just went over, where the average is 52 points and the standard deviation is 11 points. About 68% of the y values lie between what two values? Well, to begin to understand that, we have to recall that 68% of the scores, this 34 and 34 in the red shaded areas, are between one standard deviation below and one standard deviation above. So if the mean is 52, one standard deviation below would be 52 minus 11, which is 41. And one standard deviation above would be 52 plus 11, which makes 63. Now the z-scores are, because you're one below and one above, minus 1 and plus 1. Now about 95% of the y values lie between what two values? Well, I have to subtract 2 standard deviations and add 2 standard deviations to get to be within 95%. In other words, from the border of the purple and the green on both sides. Okay? So if I do 52 minus 2 11s, 2 times 11, I get 30. And if I do 52 plus 2 11s, I get 74. Okay? And what are the z-scores? This time, the z-scores are minus 2 and plus 2 because I'm down 2 standard deviations and up 2 standard deviations. Finally, and you can notice the pattern here, right? 52 minus 11 is 41, minus another 11 is 30. 52 plus 11 is 63, plus another 11 is 74. Now it wants between 99.7, and for that I need to go out one more level on the normal curve to mu minus 3 standard deviations, and on the other side, mu plus 3 standard deviations. Notice what I did on the curve here, just to help us out. The mean, mu, was 52, and then to the right side, I just kept adding 11. 63, 74, 85, 96. That's what happens every time I go up by a standard deviation. What do I get when I go down by a standard deviation? I go to 11, to 30, to 19, to 8. So that's how I arrive at the values of the curve and the normal curve. And it's very helpful a lot of times to fill that data in, because then they'll ask you a question like questions, well, A or B, but in this case, letter C. About 99.7% of the y values lie between what? 2 x values. Well, that would be 99.7 is 3 standard deviations below and 3 standard deviations above. So 3 standard deviations below are 19 and above is 85. And you can see the pattern. 41, 30, 19, you're going down by 11s. 63, 74, 85, you're going up by 11s. Or you could just look at the table, or the graph, I'm sorry, and say to yourself, look, 3 standard deviations below is 19, 3 standard deviations above is 85. And if I add these percentages in between, they add up to 99.7. All right. Now, what are the z-scores? Minus 3 and plus 3. Okay? Let's tackle one more question here. Okay, let's do a little stop and start. Go ahead. Okay. So, it says it has a normal distribution of 25 and a standard deviation of 5. So 25 is my mean. I put that in the middle of the graph. If I go down 5, I get 20 for the average, the mean minus 1 standard deviation. The mean plus 1 standard deviation is 30. And in between the 20 and the 30 is the rose-colored shaded region, which is 34 and 34, 68% of the values. Okay? So the answer would be between 20 and 30. All right. We'll get started on a new video to discuss the next material, which is pretty involved.